The next presentation is by Research Assistant Professor Sean Birkel. I'll just give you the formal component that he provided for me, and then I'll provide a couple of personal words because I'm fortunate enough to know Sean fairly well. But here's the official part, and then I'll give you the real story. Sean Birkel is a research assistant professor with expertise in climate and ice sheet modeling. His varied interests include ice ages, modern and historical climate, environmental sustainability, and data visualization. Since early 2012, Sean has been building Climate Reanalyzer, a website that provides access to climate models and weather forecasts and historical weather station data. Although most of Sean's work is computer-based, he has also participated in field research projects in Antarctica, New Zealand, Iceland, Western U.S., and here in Maine. That alone makes him a very unique person, to be a person who can handle large amounts of data and who also has a lot of experience in the field. Sean is a very interesting fellow. He got his bachelor's, his master's, his PhD, and did his postdoc with us, all at the University of Maine. He's now a research assistant professor. He has an amazing love for Maine. He will be the new state climatologist for Maine. Many of you will be seeing him in that capacity. And when we were looking for a person to become a postdoc in climate modeler in the Institute, and I was approached by some of my colleagues. I certainly knew that Sean was in the Institute and knew that he had a lot of talents, but I was reminded by his former advisors, George Denton, Brenda Hall, Peter Coons, that this was a person who was able to take large pieces of data and put them together and put them onto Google Earth, a variety of things. And I thought, oh, that's very impressive, but I didn't actually realize the potential that he had and has now clearly realized. I was smart enough, being smart in this field is a matter of associating yourself with very good people, smart enough to bring Sean with me to Cambridge, England for a meeting. We saw this amazing data that we had never been able to look at before because there was no way to actually handle the data. We'd been waiting years to actually get our hands onto this data, and Sean and a couple of colleagues and I went out to a pub in the evening in Cambridge, which of course you have to do. And I said, wow, this is just amazing data, and the way they put it together is phenomenal. And Sean, in his very low-key way, said, oh yeah, it's really good. And I said, oh, you don't seem to be too terribly impressed. He said, well, I think I could do something similar to that. Well, the bottom line is that while other groups had taken 5 years to put things together and had done a wonderful job, Sean was able in 3 months to put together the first basis of Climate Reanalyzer, which you will see. It is an absolutely phenomenal way. To me, it's like a video game. You can sit in front of your TV and you can see how the climate has changed in the places that you live. You'll see the full breadth of this. It is remarkable. If there are data sets that you know of that are not on Reanalyzer, tell Sean, he'll put them on. It doesn't matter what the format is. It doesn't, as long as it's been vetted and they're good data sets. And that is the purpose of Climate Reanalyzer, is to gradually embody more and more data sets. And they are in as transparent technique or arrangement as one could possibly have. If you want to teach yourself about climatology, you can teach yourself about climatology using Climate Reanalyzer. So Sean's presentation is about an hour. The first 30 minutes before you actually get to see the live Sean is going to be a YouTube video that was put together by Media Services, Adam Kuykendall and Ron Lisnet and others. And this is going to be something that will be available on the web, so if you don't get everything in it, you can go back to it. It's a tutorial for all of the components that now make up the climate adaptation and sustainability planning system for our work. So we'll start with the movie, and then Sean will come up. He'll give a presentation, and we will have time for specific questions and answers related to this. Thank you.
The state of Maine is rich in natural resources. Over the past century and a half, the climate has warmed, and in response, Maine's forests, ecosystems, and communities have begun to adapt. But as human population grows and the needs of society have become more complex, it is increasingly important for community leaders and resource stakeholders to plan for the future and have access to historical climate data and model predictions. Through our Climate Adaptation Sustainability Initiative, or CLAS, the Climate Change Institute and the University of Maine aim to assist community adaptation planning by providing information and software tools.
Hi, I'm Sean Birkel, Research Assistant Professor with the University of Maine. Over the next few minutes, I'll show you how to create community plans using our Climate Adaptation and Sustainability software. Sit back and enjoy the tutorial.
We've developed 3 online utilities: 10 Green, Climate Reanalyzer, and Climate Layers. Ten Green provides access to public air quality data for U.S. cities and ranks the environmental health of a given place from 1 to 10 based on EPA measured pollution metrics. You can find the 10 Green score for a town or city by entering a place name into the search field at left. How does your community score? Let's use Orono, Maine as an example. On the left panel, you can see that Orono scores a 6. This value is calculated from the nearest monitoring station within a 100-mile radius of the town. You can see on this page a list of 10 EPA measured pollutants, including carbon monoxide, large and small particulates, ground level ozone, nitrogen dioxide, and others. Pollutant measures in compliance with EPA health standards are shown in green. Measures in non-compliance are shown in red, and measures for which there are no data are shown in gray. Orono receives a 10 Green score of 6 because 6 out of 10 pollutant measures are in compliance with health standards. Click on a measure to see the pollutant description, scoring details, and health implications. In this example, I'm choosing nitrogen dioxide. Click See Map in order to view monitoring stations. Green dots indicate compliance, red dots indicate non-compliance. Click a monitoring station to see pollutant sampling details. Now let's get back to Orono's overall 10 Green score. On the left panel, click Score over time to view plots of healthy, unhealthy, and missing measures, shown in this case since 1980. We can see that pollutant measures with no data have decreased, unhealthy measures have stayed roughly the same, and healthy measures have increased. This is positive. I encourage you to explore 10 Green and to see how your community scores. Now we'll move on to Climate Reanalyzer. Reanalyzer is a program that provides access to models, historical station data, and weather forecast graphs and animations. The website has several sections, all of which are listed here on the front page, and also on the pull-down menu at the top of content pages. Perhaps the most visited page on Climate Reanalyzer is today's weather. Here you can find the current global weather forecast for several metrics. The first image that you see is for the temperature departure from average relative to the 1979 to 2000 climate baseline. You can see at a glance areas that are warmer than average versus areas that are cooler than average based on whether or not the colors are reddish or bluish. You can cycle through these images and see different parts of the globe. Then if we scroll down, we can also see a breakdown of the temperature departure values, or anomaly values, for different regions. The world, Northern Hemisphere, Arctic, Tropics, Southern Hemisphere, and Antarctic. Other metrics that we can look at include sea surface temperature, precipitation, precipitable water, which is a measure of humidity in the atmosphere, or moisture content, surface wind, jet stream, cloud cover, and snow and sea ice. Climate Reanalyzer also has weather forecast maps and animations. On some devices, images on this page may appear too large to fit on the screen. If this is the case, use the zoom feature on your web browser to shrink the viewport. Once you're satisfied with the image size, select the forecast domain. You can cycle through several of these. Select the variable that you would like to view. and then hover the cursor over the forecast hour. Some of these forecasts are 7-day with 3-hour time steps. Other forecasts are 2-day with 1-hour time steps. In any case, you may animate these by using the playback controls. Here now I'm pressing play, changing the animation speed. Be mindful that on low bandwidth connections it may take some time for images to load. If you're on a high bandwidth connection, you should be able to see a nice smooth animation. Here's a 48-hour forecast of the United States. This shows precipitation partitioned into rain, snow, and there's also cloud cover. There's a lot to see on forecast animations. Look on the right side of the domain. That's Hurricane Gonzalo, a Category 4 storm. There is one more way to check the current weather forecast on Climate Reanalyzer. It's simple. Enter a place name at the top right, Warren, Maine. Click Search Weather or press Enter. And now you have a 5-day forecast from the NCEP Global Forecast System model. At the top is temperature and precipitable water, cloud cover, precipitation. At the bottom, wind speed, sea level pressure, and a location map. Now we will return to the site index. So far we've discussed mostly the weather forecasting capabilities of Climate Reanalyzer, but for adaptation and sustainability plans you'll want to use other aspects of the site. So now we will focus on historical station data, this link here, and climate reanalysis maps and time series. First we'll go to the historical station data. From this link you come to the interface that provides access to the Global Historical Climatology Network. Here you can search for stations in order to plot temperature, precipitation histories for a given site. And this is one aspect of Climate Reanalyzer that should be particularly useful. I'll search for Portland. And in just a couple seconds, a list of all matches to your search comes up. And depending upon the station you search, you may find the entry you want at the top of the list, or it may be buried down some number of lines. In this case, I know beforehand that I want to see the information from the Portland International Jetport, which is item number 10 here. We can look at the latitude and longitude to make sure it's the station we want, and also the start and end date. This particular record goes from 1940 to 2014, and then here are the variables. It includes temperature, minimum, maximum, mean, wind, snow depth, precipitation. Select the item, and now through this interface you can create plots. Over here, select the parameter. In this case we'll go with mean temperature. Year 1 and year 2, that's the range the plot will produce. Click plot, and in a few seconds we'll see the mean temperature for the Portland Jetport. Now here's the entire record, and you may want to make your own plot, and if that's the case, scroll down a little bit and click Get Text. And now here's an ASCII text file that is nicely formatted to work with any spreadsheet software. You can download this file, import to your spreadsheet software, and then produce your own plots. There are time units, including year, month, day number of the year, from 1 to 365, and then these columns here, there's one for each variable. Now let's return to the GHCN plotting interface. We just plotted up temperature, and now let's try a couple other plots. This time, precipitation. We'll again plot a time series. Click plot. Of course, it'll take a couple seconds for the image to show up. And now, say we don't want to import the file to a spreadsheet, but we want to create another graphic on Reanalyzer. Say we want to look at particular years in which there may have been an event of high precipitation that you're interested in. Here, for example, between 1988 and 1984, there are a number of years in which there were high precipitation events, and we can change the range of time values on the plot from, for example, say 1985 to 1995. Click plot again, and now the image that comes up, we can see a little more detail. And of course, you can keep zooming in on this way. We can also plot the mean annual cycle or seasonal cycle by selecting this button here. Now in this case, I'm going to go back to temperature. This time I'll take maximum temperature. Now I should emphasize these are daily average values. In the case of precipitation, they're daily total values. We'll click plot. And once again, a moment later, the image appears. And these are the daily data for the period 1985 to 1995. Now, if we would like to see the entire record, all we need to do is select 1940, 2014. When I click plot, all of the data for the entire record period will show. Now, let's also see a daily average. I'll click this box. It says show average, and we could also overlay a particular year. Let's overlay, I'm going to pick a random year here, say 1996. Click plot, and the image that comes up again will show all the data. It will also show daily average, which is this light blue line, and the curve in orange is 1996, as we've selected there. Now you may want to change the y-axis scaling. Select this box. For minimum, I'm going to enter -20. And this for now is in degrees centigrade, but soon Reanalyzer will have an option to translate to degrees Fahrenheit. For the time being, you can do that in spreadsheet software. Click plot, and now the image that comes up will have a more appropriate scaling, in which we can see more of the data in greater detail. You may also want to get a PDF. It's a vector-based PDF file that you could easily put into a report or into any software that will modify vector-based files. Now let's return to the Climate Reanalyzer main menu, now that we've had an overview of how to use the GHCN interface to collect station data. Click Home, back at the front page, and I mentioned before that we would also investigate climate reanalysis maps and time series. We'll start with maps, and I'll define climate reanalysis. A climate reanalysis model is very similar to a weather forecast model, except for it's one that has been run back in time with boundary conditions, data supplied from a global array of weather station data, weather balloons, satellites. Those provide information for conditions at the surface and conditions through the atmosphere at any given time. The reanalysis model is run. It's a dynamical model. It computes changes in weather throughout the column of the atmosphere and across the grid. Most reanalyses are global in scale, some are regional. In Climate Reanalyzer, the name is derived from reanalysis. Now in this particular interface, again, it's used to make maps. We can make maps of temperature, precipitation, wind, over some range of years and over different domains. I won't show you every data set, I won't show you every option, but I want to give you a sense of what is available. The items on this list include reanalysis models. There's also a statistical interpolation model for temperature and precipitation. And towards the bottom of the list, there are general circulation models that are their future GCMs that predict temperature and precipitation to the future. We'll look at those in a moment. First, let's begin with this very first data set called the ERA interim. That's a reanalysis. It goes from 1979 to 2013. And this will at least give you a flavor of what a reanalysis is. For region, we'll keep world selected, click plot, and in a few moments you'll see a temperature map of the globe for 1979 from this reanalysis model. The values here are it's an annual average for 1979. We could also average across a range of years, say for the entire record period from 79 to 2013. We can also produce difference maps. In this case, I'm again going to keep ERA interim selected. We're going to subtract one range of years from another. We'll use 2001 to 2013, and from that we'll subtract 1979 to 2000. This is the climatological period that I use for the daily temperature anomalies on Reanalyzer. We'll keep it on mean temperature. For month, we can choose a specific month or a season. This would be December, January, February, winter in the northern hemisphere, spring, summer, fall, and so on. Leave it on annual. We'll change the map projection. We could also select globe, but in this case I want to keep it on map. Under region, we'll select northeastern US, click plot, and the image that comes up will show you the temperature difference from from 2001 to 2013 minus 1979 to 2000. This is on an annual average basis, and the temperature here is in degrees. In the future there'll be an option to convert these to Fahrenheit. As you can see, the reanalysis indicates that the entire region has warmed over that time period, with the exception of a small cold anomaly offshore in the Atlantic. Now, as one other example of what we can plot, precipitation, and this time I'll change the plot type to average. This will be a regular plot, not a difference plot. This will show the total annual precipitation on average from 2001 to 2013, and these totals are in meters water equivalents. And now let's produce one more map. In this previous example we used the reanalysis dataset ERA interim, and for the next example we're going to use something different. We'll select the last item on the list, CCSM4. That's one of the future general circulation models. Select that. We'll change this to temperature, mean temperature. And for projection, let's change it to globe so you can see what this image will look like. And for region, we'll say North America. And for the year, first for the year span, we'll say single. And just for fun, let's go up to 2050. Click plot. The image that comes up will of course show the temperature predicted for 2050, global projection centered on North America. And now I note that with CCSM4 there are a range of years from 1870 up to 2100. There's a historical run, a modern control run, and then of course the future run. And I encourage you to take time, play around with the interface if you will, make difference maps, and explore the changing climate on your own. It's really quite fun to do and quite interesting. You can learn a lot from these reanalysis and general circulation models. Now with that, we'll go back to the front page, and now we'll click on time series, the reanalysis time series. Through this interface, we can make time series plots of the same reanalysis data sets that we saw in the map interface. One thing I like to point out before producing a plot is that if you are uncertain which data set to choose, and there are many, and it's a daunting task if you are unfamiliar with reanalysis and GCMs, if you click the Info button here, it brings you to the Available Datasets page. Every dataset that is available on Climate Reanalyzer, by dataset I include climate models and also weather forecast models. Each of those that's available on the site has a short description here and a link to the original data source. And so if you find yourself using Climate Reanalyzer and wondering which reanalysis to use or which dataset, refer to this page, and with luck we'll answer some of your questions. Now, we'll go back to the time series interface. We'll leave it on the area interim. This time we'll plot sea level pressure. For something different, we'll plot it for May, and we'll select a region. We will this time say North America, so in this case we'll average across all of North America. Click plot. And a few moments later, we'll see an image that depicts mean sea level pressure as it varies through time for the month of May for area interim reanalysis. And again, several different data sets to choose from, including the future GCM. Now we'll select CCSM4, which we saw in the last map example. We'll click mean temperature. We'll change this back to annual. North America, we'll see the signal of mean annual temperature average across North America for the entire CCSM4 record period, which in this case it's the historical run beginning in 1870 as the modern control run in the 2000s, and then the 100-year future climate projection. And there we go. Now if you'd like to get a time series in ASCII text format, under Downloads, click Text. And just as you saw through the GHCN station data interface, you can also get a nicely formatted file that you can import to spreadsheet software if you want to produce your own plots. Here, everything is organized by year and then months. And with that, we conclude the tour of Climate Reanalyzer, and now we move on to Climate Layers. Climate Layers is a GIS-style framework for visualizing climate in relation to other environmental parameters. There are many available layers, including temperature, precipitation, land cover, as shown here, population density, conservation areas, and others. There are a number of different things that we can look at here. First, I'd like to point out, as with any good layers program that you find on the web these days, we can zoom in, and we can have state borders, county borders, and right now we have land cover, land use map up, showing the different zones, and here's a key over on this side. If we remove this layer, we can look at the base map underneath. There's Bangor. We can look at surface landforms. For example, again, here's the key. Superficial lithology, or the rock type. Percent canopy cover. wetlands. For this field, we have to zoom in pretty far. There we go. And perhaps most importantly, climate layers. We can look at temperature. We'll zoom out here. These temperature maps are for the entire United States, but of course in this presentation we'll focus on Maine. Precipitation, and we can also look at temperature and precipitation for future GCMs. Several other fields that we can look at include population density for 1990, 2000. We can look at Maine climate zones. I'll remove the underlying precipitation fields. Zone 3 is along the coast, the coastal zone. The second zone is the interior of the state, and then the northern and western mountain climate zone or division. Conserved lands. Deer wintering areas, shown orange. And also schools, police stations, fire stations. We hope that this will assist you with your planning if you need a map in which you want to overlay climate fields and then in relation to important public services. There are also hospitals can be plotted, airport runways, railroads. There are many different fields and climate layers, a number of different things to do, and as with Climate Reanalyzer and 10 Green, I encourage you to explore the software package and to see the many different things that it can do. Now we'll zoom out and we'll explore the base maps further. Different base maps provided by Esri, and I should note that the datasets included on here are all publicly available, and visit the CLAS website to find references to each dataset. This concludes our tutorial. We hope that you find 10 Green, Climate Reanalyzer, and Climate Layers useful in your adaptation planning.
I hope that was enjoyable. Of course, anytime one assembles a video of some sort, for myself, I kept seeing parts, I could have changed that, I could have said something a little more succinctly, but I'm pleased overall. I hope that you do find that useful, and as Paul had mentioned, it'll be placed on YouTube. The video will be placed on YouTube. There'll be a link on the CLAS website, and you'll be able to reference that. And I'm sure that in the future we'll have more software tutorials. One thing I'd like to note is that these software applications, maybe I'll say apps, that's what people say nowadays, they're in continual development, and you'll see over the coming weeks and months, if you go to the site repeatedly, you'll see changes, improvements, and particularly if you go to Climate Reanalyzer, you'll find an email address. And if you have suggestions or data sets that you'd like, as Paul mentioned, send an email, and we'll see if those can be implemented. Now for the next few minutes, what I would like to do is discuss the climate models a little more, because that's something in adaptation planning, there's a lot about future projections, and I mentioned reanalysis here in the video, and I described reanalysis a little bit, but I thought it'd be useful if I went over some details about climate models, and that may help you gain a better sense for what they are, how they work, and why we might trust them and build plans off of them. And then with the remaining time, I'll show a couple of examples and of course take questions. Of course, we saw these three apps: 10 Green, Reanalyzer, Climate Layers. And one thing I'm really fond of are the animations. As Paul mentioned, it's in a way Climate Reanalyzer and the other software pieces are like a video game, and certainly the animations. When I was in high school, I used to play a lot of video games, and I had dreams of becoming a video game designer. And as it turns out, I actually had a couple interviews with the software company, but then I decided, nah, I'd rather become a geologist. And I stopped playing video games cold turkey within the span of about a week after becoming a geology major, and I discovered the love of hiking and the outdoors, and I pursued that with a passion for quite some time. And then when I got to graduate school, I rediscovered programming, and that became an integral part of my research. And Climate Reanalyzer it developed because I had this existing experience with playing video games and programming, and there's the short story. This animation here, it shows temperature. It's a forecast animation downloaded right from Climate Reanalyzer. And I think aside from adaptation planning, for educational purposes, these animations are great. You can learn so much about the climate and about weather just by watching the fluid motions. The atmosphere is a fluid, the oceans are a fluid, and to see them in motion, you can really get quite a bit of insight. I do have a couple of boring text slides in here, but I think that you've seen a lot of visual stimuli, so we'll keep it simple for a couple slides. Climate models. There are several different types. The three main types include weather forecasts, which we're all familiar with from the nightly weather forecasts when you go onto weather.com. Reanalysis, I mentioned that in the video. Just want to emphasize that reanalysis models, of which there are several. They are used to investigate recent historical changes in climate, both near the surface and throughout the atmosphere, at different pressure levels, all the way to the jet stream and even above the jet stream. They're reinitialized every 6 hours with actual station data from weather balloons, and also satellites. And so they closely reflect reality. They're not perfect. All models are imperfect, but reanalysis models, particularly the ones developed in the last few years, are quite good, and they are very useful tools for investigating climate. And this term has been said a few times now, including in Ivan's presentation. GCMs, or general circulation models, also called global circulation models. A GCM can be a model of the atmosphere or of the ocean, or both, a coupled model between the atmosphere and ocean in which the dynamics between the two feed back on one another. And these are particularly important for investigating or trying to interpret what might happen in the future. We use these future GCMs, or future general circulation models. I'd like to say, and I think we all have a sense of this, the changing climate there are nonlinear systems. Many different nonlinear systems are all coupled together. And so to predict what might happen in the future, given changes in greenhouse gases, changes in land use, it's really important to use a dynamical model with with equations that describe these phenomena, and also physical interpretations or parameterizations that try to approximate how these processes work. And at the very bottom of the slide, I mentioned the other types of models, which include sea ice. Sea ice models can be embedded within general circulation models. Vegetation, land use. And again, I'm sure you've all heard of the future GCMs, and probably most of you have a reasonable idea of how they work. But if not, I thought I would show this slide just to indicate Over in this panel, for example, the discretization or the gridding of these models. We climate modelers think in terms of grid cells and pixels. The equations operate on a box, and there's heat and moisture that goes into the box, some goes out, and these boxes are all tied together, and it's all a big solution of differential equations. They're different resolutions. Typically, a higher resolution model can have more robust, the higher the resolution, the better certain processes are predicted, including precipitation. We all have a sense that it rains more in the mountains because of air pushing up against mountains, and more precipitation falls. It's an orographic precipitation enhancement is what we would say. Now these models, I mentioned that they are not just for the surface, but also throughout the column of the atmosphere. The models are gridded at the surface horizontally and also vertically. Resolutions for reanalysis range from 30 kilometers horizontal spacing to 250 kilometers, and the future GCMs are more on the line of 150 kilometers to 200 or 300 kilometers. I've already said quite a bit about the GCMs now. One thing to note is that unlike reanalysis and the weather forecast models, there's not much, there are no 6-hourly data ingests. A GCM is initialized once at the start, then it has to be tuned so that over a modern control run, the climate attains something close to a steady state, and a reasonable Earth-like climate is attained. And then once the steady state is attained, and on the broad scale it looks like a reasonable climate, then we can change the knobs, change the radiative forcing from greenhouse gases, change the land use, have a volcanic event that injects sulfur into the atmosphere, and see how the model responds. And one thing, when I first began getting into or learning about climate models, I was really surprised that they integrate the equations over seconds to minutes. And so for a 100-year simulation to the future, it's really predicting weather over 100 years. And it's projecting a very long weather forecast. To give you an idea of how a GCM might compare to reanalysis, it comes pretty close. This is reanalysis at the top. This is the average annual temperature between 2005 2011, and then here's a GCM for the same time period, but again it was initialized at some time in the past, and in this case initialized 1870, and then the model is run with the known greenhouse gas forcing, or at least assumed greenhouse gas forcing, volcanic forcing, and so on. There are differences, and there are many different GCMs, many different reanalyses. Some are more similar, some are a little more different, but they're all about the same. But you can see in this case, there are differences. But nonetheless, it is some reasonable reproduction of climate. Precipitation, everyone wants to know about precipitation. And as Ivan mentioned, precipitation is one of the more difficult parameters to predict, because precipitation arises from such complex processes, including the orographic uplift of air against mountains. It's also scale dependent. We know that in the summertime, during a thunderstorm, there's convection, thunder cells form, and that sort of process occurs at scales of about 4 kilometers or finer, 1 kilometer even. And so, as you can imagine, a general circulation model that has 100 to 200 kilometer grid spacing doesn't do very well with convective precipitation. It has to be parameterized. There are assumptions that have to be made. But then there's large-scale forcing, fronts that come through with the arrival of a new air mass. Reanalysis on the left, GCM on the right. You can see that they're a little different. So the precipitation band is a little closer to the shore in this particular case. versus farther offshore. But in general, the patterns are reasonable, and the GCM is doing something right. IPCC, Ivan defined IPCC, Intergovernmental Panel on Climate Change. Several reports have been released since 1988, and this is a body of literature and models that we generally use to in trying to assess what might be to come in the future. One thing that, in terms of trying to understand how these models work, it's important to understand how many models there are. In IPCC, there are, depending on which report, there's 6 to 7 different groups, international groups, that have developed their own GCMs with their own physics, own physical parameterizations. And each of those GCMs is run in an ensemble of 5 to 7 members. And then those ensembles are, well, they form an ensemble average to try to get at a climate statistic. And then there are different scenarios. I'll skip this slide for right now. With the 2007 release of IPCC as an example, here's the CO2 forcing on the left, the temperature response on the right, and then the colors indicate the different scenarios. There are the scenarios in which greenhouse gases are curtailed in the future, or they continue to rise, a business as usual scenario, and then the temperature response. But what I wanted to get across is there's a vast number of these models, many different ensemble members that have to be averaged together, and then there are several different scenarios. And so we're talking about dozens and dozens and dozens of these models, and it's quite striking, but it's not something that it's quite at the forefront. So an enormous amount of work that goes into trying to predict how the climate will evolve. And these models can be run in the past too. Part of what I do is I study ice sheets and ice ages, things that happened 20,000, 100,000 years ago. Their GCMs have been run for the period of the last glacial maximum, roughly 18, 20,000 years ago. The same models that go into IPCC, same physics. These two plots here show the latest IPCC, AR5, representative concentration pathways. It's a little different. They can take a different approach. They've developed different scenarios, but the models work in a very similar way. And going from curtailing emissions versus more of a business as usual scenario of high emissions. And then a plot from Climate Reanalyzer showing the temperature response for RCP 8.5 on the high emission scenarios. Before I say thank you, Mark, could you switch to the webpage? Just wanted to go back to Climate Reanalyzer real quick and show, say a couple more things about that. If you're interested in using these models, say if you want to produce a difference map of temperature or precipitation across the future projection, or if you want to investigate what's happened in the last 30 years or so, you can again refer to the various interfaces on Reanalyzer, including maps and GCMs. And I don't have the computer right here, but you can change the parameter, the month, the plot type, data set, range of years, and then of course produce a map. But what I wanted to point out was you can also click that little checkbox that says Google Earth, and anything you plot on the map interface, you can get a nice KML or KMZ file that can open in Google Earth. And Mark, if you could now switch to Google Earth. As an example, here's sea surface temperature. This is for yesterday. And if you could just, Mark is just going to rotate the globe just so you can see. But in this case, you can see the individual grid cells of this particular model to give you a sense of the resolution in relation to the Earth. But it's a video game. And with that, I'd like to take any questions you might have. Yes?
Did I understand that the AR5 is the latest IPC model?
Yes, AR5 is the latest. And something that I find amusing, the models are used in AR5. They're part of what's called CMIP5, the Coupled Model Intercomparison Project. But AR4, the 2007 release by BCC, used CMIP3. And my understanding is there's now a CMIP6, and I think it's going to go along with AR6. Yes?
Can I just ask, when people ask questions, that you kind of let one of the microphone folks come to you so that the rest of the group can hear? I don't know if it's going to come. If you want to go to it, or you guys can bring the microphones out to the place.
As a layperson who might use the Climate Reanalyzer site, and knowing that we all have short memories, I would like to be able to, so maybe you can tell me how to do this. For example, if I say, boy, this October seems a lot warmer than it used to be, and I want to go in and see that in fact this October is on average warmer than 2 years ago, 5 years ago, 10 years ago. I think I understand how to do it, but I'm not quite sure. But I think that's a useful thing when I'm talking in my communities with people who are only thinking 2 years ago and saying, oh, it's a lot colder, to compare it to, say, the last decade or 25 years.
That's a very good point. And if you use the reanalysis time series page, oh, yeah, if you go to time series, and if you could just select October. Some of these data sets are updated almost immediately. Others, the reanalysis, I tend to update every few months. I'm really trying to have things updated more readily, including the GHCN, the Global Historical Climatology Network. Right now it shows just the daily values, but I'm also integrating the monthly averages. And long story short, very soon all these data sets will be updated within the last month. But in general, you can go to the time series plotting page, select a reanalysis data set, the month that you want to plot, and of course select a given region. You can select the Northeast, it's one of the predefined options. And there's a time series.
I don't think I need to like, based on facetious, but for those of us trying to work closely with our community to prepare adaptability in our community for general resilience in our population, is there a mobile app?
Well, for the most part, this site is accessible from a smartphone. Although I myself don't have a smartphone, but I have used one, and the first thing I did, can you go to Climate Reanalyzer for me? It actually looks pretty good. Ideally, we'll get some more help with the software development. I have had a little bit of help. There have been 2 undergraduates in the last couple of years who've helped during the summer, and then now there's a graduate student who's working with me. But the software development can go on and on. I could spend the next 10 years working on afternoon projects. But that's an excellent point. That's something I'd really like to do, is have a specific dedicated app for, say, phones or tablets. Thank you.
Thank you very much. I should also point out that on Climate Reanalyzer, there are 2 ways that you could look at Maine or the community. You could either zoom in on one of those global maps, or you can put in your own coordinates for the area that you live. So while Sean was showing you really global approaches to this, you can take it right down to the small scale, overlay it, and what you have. So you now have complete access to all of the chemical and physical data that anybody on the planet uses for climate research. I can't overstate this more. I do not believe that there is actually, I know for 10 Green, because we've been looking for years, there is probably nothing that recreates the amazingly fine EPA data set that's available. And there, Sean patterned this particular system after the NCEP NCAR Boulder, Colorado system, but it's actually, it has even more on it than their system does, and it's easy to upgrade. So that if you find data sets that you are missing or should be on there, please tell us. It's a remarkable data set. We don't necessarily assume that everybody is a climatologist, but for example, if you want to be able to talk to somebody who comes from Nebraska, and they say that they don't really know if there's anything that's happened in Nebraska, you can immediately tell them how the air quality has changed, you can tell them how the precipitation, temperature, et cetera, et cetera. So this is an absolutely iconic opportunity to access tools. I mention the word iconic on purpose because our next speaker, Esperanza Stancioff, is in fact an icon. She's known to many people in the state. How many people in this room know her? Raise your hand. Yeah, so probably more than anybody else in this room, people know Esperanza. She's a premier climate change educator, works with Cooperative Extension, Maine Sea Grant, and is, along with Cooperative Extension, many other people in Sea Grant and Cooperative Extension, is going to be one of the ways in which we get this information out to people who are not at this conference, number one, or people who've been at this conference and others who say, well, this is great, you've got all that data, but I'm not entirely sure how to use all these things, and a little bit more help. This will come from people like Esperanza. She's worked at the University of Maine Cooperative Extension for 26 years, designing and implementing outreach, applied research, and educational programs for high priority areas in marine and coastal ecosystems. She's a member of the Marine Extension Team, a collaboration of Maine Sea Grant and UMaine Extension, currently serves as lead for both organizations in climate change adaptation, and is co-chair for the national and regional Sea Grant climate networks. Projects include a number of adaptation efforts focused on reducing climate-related impacts through infrastructure improvements and tailored design support tools to promote economic development and secure communities via several funded NSF and NOAA awards. She's also co-developer and coordinator of Signs of the Seasons, a New England phenology program. So I'll turn it over to her.
Good morning, everyone. Morning. Thank you all for being here. I think I have to turn myself on here. Can you hear me? Yep. You hear me in the back? Yeah, okay. All right. So thank you for that lovely introduction, Paul. And I'm really happy to be here, and it's great to see that there are so many people that are interested in braving the weather to come and join us in this effort. So I just want to recognize, as Ivan did as well, that there's a lot going on in climate adaptation in Maine. What I'm going to do is simply do a very broad brush of 4 projects that get at a lot of different things working in community. And as was said, I work really in the communities and enjoy very much the interaction that we have. And it's really looking at the social, the economic, and the environmental, where that nexus is really an important part of this work. So these are just some of the, whoops, that's, okay, I gotta do both. All right, sorry. Okay, I gotta multitask here. So these are the likely foreseeable impacts and effects that I'm going to be sort of in talking about within the projects that I'm going to be giving a slice of. And so what are the impacts in the Northeast as far as fisheries go? Oops, there we go. Well, lobsters are affected by oxygen levels, and we know that warmer water holds less oxygen, and it actually becomes insufficient for lobsters beyond 79 degrees Fahrenheit. In the north, we are expecting that warming is improving lobster habitat, but the jury's still out on that one. In Maine, the shedders that were reported by fishermen were a full 3 weeks or more earlier in 2012. You heard this from Ivan, and further offshore. So our fisheries are in motion. Oysters, the deadly disease that has been expanding itself northward from Chesapeake Bay to Maine, and the shift is linked to above average winter temperatures. Shellfish is affected by ocean acidification, as we've all heard. This is a great, oh, I gotta keep doing this, all right, I'll get it together. This is a great image that Rick Wally put together that really shows the difference in how groundfish were reigning supreme from 1950 through the 80s, and now, of course, lobsters are sort of almost our monoculture in Maine. So just to talk about something that's really important for Maine is that our coastal climate is really connected, very closely connected to the currents. And this is figures from a manuscript and review that Dave Townsend kindly let me use that shows the sort of the blending effect of the currents in this figure. And in this figure, it shows how, of course, we have sort of a sea within a sea, and a lot of different factors go into how our climate is affected by sea temperature, Arctic ice melting. The Labrador Current is actually the current that brings the cold water in from the Arctic, and has more effect actually than our Gulf Stream does. And what this means also is that as the Arctic ice is melting, we're going to be impacted by more fresh water into the Gulf of Maine. So a 14-year study done by Barney Balch and others from Bigelow, U.S. Geological Survey, and others have shown that half of Maine's largest rainfall events of the century have actually occurred in the last 7 years. I'd like to see that on your reanalyzers, Sean. And documents the significant changes that have occurred in the Gulf of Maine as a result that are tied to increased rainfall and the volumes of river discharge that we have. Whoops, here we go. Sorry. And data have shown a large shift downward in primary productivity. In fact, a 5-fold decline in the growth rate of phytoplankton, remembering that it's that very special microscopic single-celled plants that form the foundation of the marine food web and ultimately supports the species in the Gulf of Maine, as well as contributing to half the oxygen that we use on this planet, and taking up a lot of the carbon dioxide as well. So the impact of this decline, while it may take several years to have an effect on the food supply of commercial fisheries, think lobsters, 6 to 7 years before this might actually hit home. So this is the graph that, whoops, here we go, that Barney has, Dr. Balch has put together, and showing that over from 2000 to 2014, even though we've had a spike in 2006 of primary productivity, it's really on decline. And as you can see, the plunge in 2014 has everybody startled and worried. This is the Nova Star Ferry and Barney in his lab, which is this container that goes on the ferry. It's a 200-mile straight line for their transect, which is pretty cool. So planning for a changing climate, we're using a participatory approach in a mid-coast community. This is the wonderful group of researchers involved and students. We had 3 graduate students involved in this project from Clark and from University of Maine. who really contributed a lot to this effort. Just to note, in Knox County, from 1995 to 2005, they were the top producers of lobster in the nation. That's no longer the case. We're pretty much they're pretty much down the list from there, and that is actually taking place more in down East Maine now. So this is a participatory process that we went through with this community, discussing a project, developing community profiles, interviewing community leaders, 18 of the lobstermen, one-on-one for an hour. We got a lot of information on what they thought about climate change, what they're seeing out there in the environment. We consider them the daily ecologists. And then we facilitated workshops, we presented climate projections, we diagrammed scenarios and validated scenarios, and we built a systems dynamic model. So basically the community profile was, this is just an excerpt of major points from that, knowing that there's been 400 years of recorded history of fish landings in that community, and a statewide decline, and as I showed from the Rick Wally image, decline of natural populations of a lot of the species that they were commercially dependent on, with the lobster fishery being the dominant one in the past 20 years. So that heavy economic reliance on lobster fishery means that the community of South Thomaston, as well as others, is particularly sensitive to a changing climate with regards to the lobster population. And it's a little bit of a scary position to be in. And they all said, you know, these are the warmest waters they've seen in 40 years. So the interviews were very helpful. We got a lot of information from them. And we went into the meeting together to start to create these climate concept mapping. And these are the different items that we started to look at, the different factors, management concern, climate stressors, and so forth. And then we put that, one of the things that came out of the climate stressors for the fishery, we did this for the community as well as the fishery, was, of course, warming water temperatures. Ocean acidification was second on their list. They knew nothing about it, very scary for them. And then increased precipitation. And we ended up focusing on warming waters primarily and ocean acidification. So looking at the climate stressors, then we started identifying those, and you know, the new species, the locations of lobsters, increased catch, and early shedders, and what do those mean to the lobstermen? And then we started putting our map together. So I don't expect you to be able to read that, but just note that all these different factors are being considered and arranged so that it makes sense to them to then start to look at the whole picture. And they really enjoyed this. It was visual, it was participatory, and they got a lot of information out of it. And from that, we started looking, from that we developed these fishery management actions that they could actually start thinking about and working towards. You know, at that time, the marketing systems for the state were starting to be considered, and so that's something that they were really interested in. Involvement in states' efforts to use license surcharge for marketing, all these kinds of things that they came up with, which were really helpful for them in thinking about their future. And then we put a lot of this information together into a qualitative systems dynamic model. There are all these inputs that you probably maybe can't read, but just for example, looking at the top purple one is temperature, lobster density, population dynamics, which goes into the ecology module, and that then goes into the pricing module. Number of traps hauled, location fished, goes into the fishing effort module, on down to, you know, the actual expenses. The Canadian processing was a big deal. The Canadian processing schedules, because in 2012 they could not get their they didn't have that access, which they depend upon. Availability of markets, U.S. Canadian and Canada exchange rate goes into the pricing module as well. And so all of this comes out, and you know, what is happening to their bottom line. Put all these factors in, change the conditions under different scenarios. How are they going to How are they going to fish? Are they going to fish, smarter, not harder? And that's Dave Cousins' quote, and it's taking hold. And so we're still working with them. We have one more meeting with them. We're hoping to get funding so that we can continue this and to start looking at policy and bring together the fishermen and the policymakers. And it's been a great program working with them, and very, very enjoyable to see their what they can provide. So, ocean acidification. It's a scary thing out there, and this just, I think Ivan probably covered it very well in his talk, but pretty easy to see as carbon dioxide in the atmosphere goes up, the pH goes down. And looking at the forecast of aragonite saturation by 2100, red is the worst, and we're in the hot seat up here, so it's not looking good. And you've probably seen the article or the video featuring Mark Green, professor at St. Joseph College, and researcher talking about dead mud, places where shellfish was productive before and they're not found anymore. And he's been working with Joe Salisbury and on looking at sediment, ocean acidification or pH in sediment. And as the rising levels of CO2 in the atmosphere combined with unregulated nitrogen pollution, it could have a severe effect on Maine's $60 million shellfish industry, meaning, like the dead mud and what's happening with the clam industry already. Maine is especially vulnerable to this due to this increase in rain events and the freshwater input, and also perhaps the Arctic melting. Freshwater has a lot more acidity than buffered saltwater does. And this adaptation needs to be done in concert with research. You can't just crush shells and put it on the clam flats, as some people are suggesting, because you don't know what that environmental effect might be in that ecosystem. And so one example, local aquaculturists in Washington State and in Maine are starting to use the incoming tidewater with normal levels of pH so that they can run their businesses in a more efficient way. So we have the Northeast Coastal Acidification Network, or NECAN, has been created to understand the science of coastal and ocean acidification. We have a dynamic steering committee of scientists, state and federal agencies, and educators and aquaculturists and so forth. And so what we're trying to do is to have a process in place where we go from education to implementation. And looking at what we've done so far is between November 2013 and March 2014, we conducted scientific webinars from researchers from all the way from Long Island Sound to Nova Scotia. And those webinars are an hour long in length, and they are on the Nearcoos NECAN website for anybody to go back and look at. And some of them are really, really great and at all different levels of science. So we also held a State of the Science workshop for 2 days, and we're planning 3 stakeholder workshops in December in Maine, and then in 2015, early 2015 for Massachusetts and Connecticut. We're taking the state of the science that we've put together in synthesizing that, then translating that for stakeholders, then getting stakeholder input that will all inform an implementation plan and strategy going forward. So, switching gears here to the coastal infrastructure resiliency in a changing climate. We have been lucky to have great support for 5 years from the Sustainability Solutions Initiative here at the University of Maine, the George Mitchell Center, from National Science Foundation funding, and the NOAA National Sea Grant Coastal Community Climate Adaptation Initiative. And we've had a really great research team engaged with researchers from UMaine, the City of Ellsworth, and the Department of Transportation. So we started this by scoping out in two very, very different communities, Lincolnville and Portland, and we were scoping what they thought about the vulnerabilities to infrastructure based on a changing climate. And we got a lot of great information, and they pretty much coincided. And then we took that information and we developed a survey that we sent out to 255 municipal officials, being sort of the gatekeepers of their communities and the ones that need to be making these decisions for municipalities. We also held focus group discussions. We also checked ourselves out to see if the same responses might be elicited from our surveys that other coastal community researchers might use. And our results really showed that, and I can put them in here, but they really showed that people were really most concerned about extreme rain event storms, both current and in the future. And culverts as the infrastructure was what we chose because all communities have them and have a need to try to mitigate some of the flooding and erosion and problems that come from poorly designed or undersized culverts. And governance, culvert functionality has a complex governance system, and it really relies on communication between local and state and federal government. So, looking at understanding stormwater culverts, if you look at these roads, the streams and then the road systems, where those intersect, there's these little red dots, which represents a culvert. I must note that finding culverts and knowing about them is not as easy as what you may think, just driving over them. But if you look at this little square here, you see no culverts. So if you zoom in on that little square, which I will do here, then you see that there are actually 7 culverts. So Scarborough is one of the only towns that I know of. I'm sure there are others, but there are very few towns that actually know what they have. So the road stream crossings, while there are 125 documented road stream crossings in Scarborough, their actual total culverts is 2,127. So this becomes a kind of a tough thing to understand. Looking at the coastal zone, there are 6,023 road stream crossing culverts, but we have no clue how many total culverts we have. However, if we look at road stream crossings along the coastal zone, then we can at least use this information to try to start thinking about the mitigation efforts that need to take place. And if you look at, this is the increase, or the ones with the most culverts are the towns and cities of York, Biddeford, Saco, Scarborough, Augusta, and Ellsworth. And then we can further use information for looking at extreme precipitation increases. And as you can see, the mid-coast area has the most, and some of the islands have the most. And down east, Maine has the least increase in precipitation increase. So we met Ellsworth at a focus group discussion that we held, and the senior planner, Michelle Gagnon, was there, and she was very concerned about what she knew and what she didn't know, and we wanted to know how we could enable a municipality to make these climate-related decisions about their stormwater management, both in the present and in the future. And if you Google Ellsworth, this is the first picture that comes up. So that was interesting. So I'm just going to run through some tools that we developed, and just a smattering of them. There are more, but this one was looking at an example of tailored information that our engineers on the project, Shalene Jane and Nirajan Dakal, worked on. And so if you look at Corinna, which is, and we did it for a bunch of towns, but this is the closest one with the rain gauge to Ellsworth. you can see that in 1950, the red is 1950 to 1980, that 30-year period, and then the next 30-year period, 1981 to 2010, is in blue. And you can see that, and this is these are the months of the year down here. You can see there's a full 2 months earlier seasonality change for extreme storm events. So occurring earlier in the year can be very problematic for management of culverts because they can be filled with ice and allow very little water to go through. So the infrastructure maintenance and potential impacts are often very sensitive to the timing of extreme events. As I mentioned, as I mentioned earlier, culvert functionality is really a complex issue, and we started investigating this with Lincolnville even before working with Ellsworth, and they actually had a pretty good governance map that we used as sort of a model. And then we started looking at all the different functionality that goes into culvert management, and looking at all the different entities that need to be communicating that we're not. And so we sort of expanded our sphere of influence as we went along, including more and more people to better understand what was going on. And there are no federal or state standards for managing culverts in a changing climate. So I think that people are definitely working on that. So this is just based on information needs. What kind of simple tools can be used to help them prioritize culverts and look at design perspective and management perspective. So basically, we did some GIS mapping for them, and this is the roads system and where culverts are located. And for example, you can look at this and think about what road might you not be able to get services to if a culvert failed. So that would become a priority area, and you can make different assumptions for this and use different layers in finding out where your weak points are and where you might want to start prioritizing and budgeting for this. Use of freeware tools, because a lot of, most towns don't have GIS capacity. It's very expensive software, and it's also very, can be very labor intensive, especially if you don't have the expertise, and which most towns don't. So we started looking at and developed a guide for putting this together in a different way on Google Earth and using Picasso, and smartphones. So basically you can look at this and you can record all of your information, and then you can order it by assumption of what the needs are. Red might mean that this is a culvert that's going to fail, so we need to get right on that. It's also a great visual tool for councils and planning and budgetary needs. So we learned a lot of lessons. This is just a smattering of those. That continual engagement for adaptation is a necessity. That governance is critical in identifying key areas that climate-related information must address in order to be actionable. And ongoing training opportunities to constantly be on the lookout for that for folks. And it's difficult to challenge conventional or current management practices, and this is an iterative process. Its adaptation is slow. Education outreach was a very big, how am I doing?
You're good, sir.
Okay, sorry. Education outreach was really important for Ellsworth, and I think it is so for most communities. And we did a lot of things like we put together an education guide that they would then put pieces of on their website and their Facebook page when a rain event like today happened. So maybe if you look on Ellsworth's site, you can find one of those pieces of education. And then we also held a community forum, and we expected about 25 people, and we had over 60, which was really encouraging, with a lot of interest. There's a lot of synergy that happened with this project. COA students actually did a whole class on GIS to provide tools to Ellsworth, And we also engaged in the production of a Maine Public Broadcasting DVD called Covert Operations. If you haven't seen it, it's a pretty good educational tool. And we worked really well with Ellsworth. Ellsworth was a great community to work in, and we're still working with them, so it's great. And we've also started working in Newcastle and Damariscotta, and they were really happy to have these tools, these freeware tools, and they're using them now. We spent some time in the field with them, actually inputting the data and showing them about that. So they're really pretty excited about that as well. Okay, so the love of my life. Ecological impacts, including the timing of biological activity, is super important when we're talking about changing climate. And phenology, it's an obscure word that is part of our daily lives. It's the timing and of the recurrence of plant and animal life cycle stages like flowering and leaf fall and migration and hibernation. Think of farmers trying to determine when they're going to harvest, and fishermen when they were going to set their traps, when we're going to experience and enjoy Sugar Maple Sunday and lilac festivals. It's all dependent on phenology. And it's also been noted that it's perhaps the simplest process in which to track changes in the ecology of species in response to a changing climate by IPCC and others. It's been in a lot of documents. And okay, so we developed Signs of the Seasons, a New England phenology program. Started out as a Maine phenology program, but we've expanded. And with the goals to increase climate literacy for Maine citizens through observing and recording the local effects of a changing climate, and to contribute meaningful data to researchers and resource managers who are trying to understand and adapt to these effects of climate change. So this is a program that is a University of Maine Cooperative Extension, a Maine Sea Grant, developed and coordinated and managed. And I have a great cohort, Beth Bisson from Maine Sea Grant, that we share this program, and have been able to have a lot of great response, and we have volunteer observers in all 16 counties and interested citizens of all ages, from 4-H youth and master gardeners and public libraries and different nonprofit organizations, land trusts, and so forth. And we have 20 species on our indicator species list, and they're easy to find. They're commonly found. A lot of calibration species. I don't think I didn't put it in there. Anyway, and we have great partnerships, incredible partnerships. We have the National Phenology Network that houses the sophisticated database that we use, and we have the National Park, Acadia National Park, and Scudic Institute is a very, very close partnership. Abe Miller-Rushing, who was the science director for the National Phenology Network, lo and behold, moved to Maine, thankfully, and is now the science director for that, and has been a great partner, as well as all of these other folks, and schools and educators all over Maine. So citizen science is the only way these data can be collected in such large numbers, and I would encourage you all to get involved. We have just a little PR here. We start doing our trainings in March. We do in-person trainings. It only takes 15 to 30 minutes of your time every week during the height of the season. And these data are being used by Boston University, Acadia National Park, researchers from all over the place. And there's an open database through the National Phenology Network. And I can't say enough about this program. It's a really great one. So with that, I will close with this quote: building on a long history of communal achievements and tapping into a yearning for community and meaning, the way we speak about climate change must become the ultimate expression of our love for land and neighbor and for life itself. Thank you. questions? Any questions? Yes.
Would you, on the top of your head, just have maybe 5 to 10 of your indicator species that are being monitored by the citizen science effort?
Sure, I'm happy to. We are, what comes to the top of my head right now, because we really expanded this part of the program, is Aspergillus nodosum, which is a rockweed in the intertidal. And we're working with Jesse Mullen at Maine Maritime Academy as a researcher. And we have a lot of great representative locations along the coast now. We have our own database in our website. And I failed to mention there's a ton of information on our Science of the Season website. If you'd like to go there, it's on the Cooperative Extension web system and has all of that information. Some others are, loons, robins, forsythia, lilacs, dandelions, wild strawberry, sugar maples, red maples, ash, and we have 2 new species, wood frogs and peepers, and toads. So there's a lot, there's certainly more. Yes?
Thanks so much for a very fascinating presentation. I really enjoyed it. I noticed that you had property values as one of the main indicators for assessing priorities. And I wondered how you include social inequality, social justice issues in your adaptation.
Right, that's a really great question. And when we went to Damerscott and Newcastle, they said, we will never use that as an assumption. And that makes sense to us. But I should qualify that Ellsworth is using it more for the business and the downtown area, and that's just what one of their assumptions was, and that's what they wanted to do. So, good question.
Hi, Esperanza. I wonder if you could tell us how you can take the lessons you learned from Ellsworth and scale that up so that you were able to work with many more communities at a little bit more rapid pace than just a couple at a time.
More funding, more people. I don't know. I think that we're obviously going for more funding to be able to do that kind of thing. And I think that one thing that we can do is to do some community meetings and talk about ways to go through this process. And actually, so let's see what comes out of this afternoon for that aspect. But I do believe that some of these tools can be useful to communities. It really gets down to, are you going to keep the buses running, or do you want to put money into some of these adaptation efforts? And I think the education value of working together with people and building those relationships can help them see, what the steps they do need to take. I'm not sure I'm answering your question, but I think that, there's a lot of other people in the room that are working on this too, so I think that coordinated effort is important. Okay, thank you.
Thank you, Esperanza. We just heard more tools and 4 on-the-ground examples of how, for particular issues and communities, people in this particular case, led by the programs Esperanza is involved in, are dealing with resiliency and sustainability. Before we break for lunch, Suzanne Miller, if you could stand up. Suzanne Miller is the regional director for Maine DEP. She wanted us to announce the fact that there'll be an International Joint Commission St. Croix River Watershed meeting on November 20th, 21st in St. Andrews, talking about climate change and community resilience. So if you are interested in the meeting, would like to learn more, speak to her, or go to www.stateofthesaintcroix.org. Thank you for pointing that out. So we will re-adjourn at 12:30 right in here. We're on schedule. We'd like to be able to finish by 5 o'clock. Since the weather's bad, I'm sure people have plenty of places to go. We'll see you at 12:30. Thank you.